Welcome to section 14.5. In this section, we're going to be looking at the more formalized definition of the chain rule for functions of several variables and dealing with partial differentiation in the chain rule. So the basic concept of the chain rule is going to remain essentially the same, but we need to account for these partial derivatives. So if we look back to the original version of the chain rule, we have a function y equals f of x, and x is a function g of t, where f and g are differentiable functions. Then the derivative of y with respect to t is equal to dy dx times dx dt. So, and if you put that in more kind of common terminology, the dy dx, this would be the derivative of the outside function. And then the dx dt would be the derivative of the inside function. And that was the basis of the chain rule, was taking the derivative of the outside function times the derivative of the inside function. So for the chain rule with partial derivatives, we're going to have a couple different versions of it, a couple different cases, depending on how many variables are involved. And then we're going to look at the general case that can apply to any number of variables. So we start off with the chain rule case 1. So suppose z is a function of x and y, so we have a function of two variables, and x is a function of t, and y is a function of t. Then the derivative of z with respect to t equals partial z with respect to x times dx dt plus partial z with respect to y times dy dt. So if we have a function of two variables and each of those variables is written in terms of one other variable, this is the chain rule that we're going to get. So we have here like the derivative of the outside, and then we have the derivative of the inside, and then we do it for x's and we do it for y's, and we add those results together. So take note of the notation here. This and this term both use the partial derivative notation because z is a function of two variables. So because there is a choice of variable, we need to use partial derivative notation. Whereas with these two, x and y are just single variable functions only in terms of t. So these are just regular dx dt and dy dt. Okay, because there is no choice of variable. It is only the single variable derivative. So we need to be very careful not to mix up these notations and be very clear about which ones are partial derivatives and which ones are just single variable derivatives. So let's try an example. See kind of what this looks like in practice here. So we have a function of x and y, and we have the functions x is sine of 2t, y is cosine of t. Find dz dt, so derivative of the outer function with respect to that inner variable, that inner parameter, when t equals 0. All right, so we're going to get dz dt. So this is going to be partial derivative of z with respect to x. So we'll go ahead and take that right now. So that's going to be 2xy plus 3y to the fourth times partial x with respect to t. So partial derivative, or excuse me, just the derivative of x with respect to t. So that's going to be 2 cosine of 2t. Plus partial z with respect to y. So we're going to get x squared plus 12xy cubed times derivative of y with respect to t, which will be negative sine of t. Now, currently we have this expression in terms of x's, y's, and t's. So we don't want to leave it in that form. What we would need to do, if it just asks for the formula itself, we could go ahead and substitute in these values for t's. Okay, so the x's become sine of 2t's, the y's become cosine of t's. And we could do that and expand out the formula. However, we're looking specifically when t is equal to 0. So instead of going through that whole process of substituting everything out, what we can do instead is, so notice, when t equals 0, x is sine of 2 times 0, sine of 0 is 0, and y is cosine of 0, which is 1. So when t is 0, x is 0, and y is 1. So we can go ahead and just substitute in these values into this formula to get our numerical answer for this rate of change, for this derivative. So dz dt, this is evaluated at t equals 0. Let's see, so all the x's will be 0, the y's will be 1. So we'll get 2 times 0 times 1 plus 3 times 1 to the 4th, 2 cosine of 2 plus 0 times negative sine of 0. I messed that one up, didn't I? That would be cosine of 0 right there. Okay. So let's see what we get here. So that's a 0. This whole thing is a 0. So we're left with 3 times 2. So 6. So the value of that derivative of z, this function, with respect to t, that innermost variable, at t equals 0, is 6. So this is kind of the equivalent of, like, if we were to substitute these functions in here at the beginning and get a really long, ugly expression in terms of sines and cosines with products and different like chain rules and power functions, all that kind of stuff, we could do that, but by setting it up this way, we're able to do it a lot more quickly. We didn't have to go through all of those extra derivative steps. We just take a couple partial derivatives and plug in the appropriate values. Looking at case 2, we step things up by one variable. So suppose that z is a function of x and y, so just like before, and x is a function of s and t, and y is also a function of s and t. So now z is a function of two variables, and those two variables are themselves functions of two variables. This is going to produce not just one single derivative for z like before, because now it's not just t, we have s and t. So we're going to get two partial derivative formulas. So we're going to have partial z with respect to s will be partial z respect to x times partial x respect to s, right? Derivative of the outside times derivative of the inside, plus partial z respect to y times partial y respect to s. And that's our formula with respect to s. Partial z with respect to t. This one will look pretty similar to the other one, so that's partial z respect to x times partial x respect to t plus partial z respect to y times partial y respect to t. Okay. So we have two of the innermost variables, so we have two separate partial derivative formulas. Notice all of these derivatives now are partials, because at every level we have choices of multiple variables to differentiate with. So let's take a look at an example with this one. So we have z is e to the x sine of y, and x and y are both functions of s and t. Find these two partials, z respect to s and z respect to t. So partial z with respect to s. So we're going to get partial with respect to x here is e to the x sine of y times partial x respect to s. So that's going to be a 1 here and then just a t squared, plus partial z respect to y, so that's e to the x cosine of y, times partial y respect to s. So we bring down that 2, that's 2st. And then to write the final form of this, we need to, since it's just asking for the formula with respect to s and t, we need to go ahead and substitute these x and y values for their corresponding functions here. So we're going to get, this will be e to the st squared sine of s squared t. See, don't really need the outer parentheses on that anymore. Plus e to the st squared cosine of s squared t. Oops, I left off that t squared, didn't I? Let me move this. So this t squared, I left this off, so I'm going to add that in here. So the t squared I'll put right there. And then the 2st, I'll put that in front of this one too. Just kind of put it in front of the functions here. So this would be our formula for the partial derivative of z with respect to s. And now put in terms of s and t. So if we were given values of s and t, we could plug them in at any point and use that to find the rate of change at that specific set of values. And then next, so we look partial z with respect to t. So we get the same idea here. And in fact, the first and third derivatives here are going to be the same, right? Partial z respect to x and respect to y. So those two are the same. These partials will change. X with respect to t, we get 2st plus then e to the x cosine of y. And then partial y with respect to t, we get just s squared. So we get 2st and then substitute in appropriate values. So est squared sine of s squared t plus s squared e to the st squared cosine of s squared t. So that would be our partial derivative with respect to t. Now, as we start getting more and more variables involved in these problems, it can be harder and harder to remember the formulas and to remember like the patterns and such. So we do have ways of helping us remember. The primary method is through the use of a tree diagram. So this case 2 that we just looked at has 3 different types of variables. So we have z is a dependent variable, okay, because it is dependent upon all of the values within it, x's, y's, s, and t's. Now I'm going to leave a little gap here. S and t, those are the variables, the innermost variables. Those are the independent variables because everything depends on them, but they have free choice, basically. We are able to select the values we want for s and t. That leaves us with x and y, which are kind of the go-betweens, right? Because s and t go into here, and whatever comes out of there goes into there. So they are dependent on these, but independent of that. So we call these intermediate variables. So one way to organize these variables is through the use of what we call a tree diagram. So the tree diagram will also help us remember formulas for partial derivatives. So we're going to start up at the top here. So we have z. Z is in terms of x and y. X and y are each in terms of s and t. And now how this can help us with our formulas is each one of these branches that move down the tree correspond to a partial derivative that connects the two variables. So this one would be partial z with respect to x. This would be partial z with respect to y. Down here, we get partial x respect to s, partial x respect to t, partial y respect to s, partial y respect to t. So, for example, if we wanted the partial derivative of z with respect to s, we basically just need to connect the paths that go from z to s. As we go down the branches, we multiply. As we go across the branches, we add. So as we go, down, multiply, across, add. So if we wanted the formula for partial of z with respect to s, we would get partial z respect to x times partial x respect to s, plus, as we go across, partial z respect to y times partial y respect to s. And if we go back up, that was this formula. Partial z respect to s, x times partial x respect to s, plus partial z respect to y times partial y respect to s. Okay, so this formula, this tree diagram, can help us develop the formula for any chain rule partial derivative. It didn't have to be s, it could have been t, and then it just changes which branches we take. And we can apply this to not only 2 and 2, we could apply it to any number of variables, even case 1, where they each just go to one variable, then you just don't have the choices anymore, and it just goes straight down each branch, and that's okay. So this will particularly be helpful when we talk about the general version of the chain rule, this version that will now apply to any number of variables, not just 1 or 2. So I've already got it written out here. So suppose u is a differentiable function of n variables, and each of those n variables, all the x's here, is a differentiable function of m variables, t1 through tm. Then u is a function of those m variables of t, and this is our general formula. Now, this is a very precise, very mathematically rigorous version of the formula. So I know it looks a little bit more complicated because of all of the different variables, the subscripts, all of this kind of stuff. But basically, u is taking the place of z. That is the outermost formula, right? And we had examples where z was a function of x and y. That would be these intermediate variables here. So that's x1, x2, x3, all the way through xn. Those are the intermediate variables. And then all of the t's here, t1, 2, 3, all through m, those are the independent variables. So they're like s and t in the previous example. So what we're doing is with t sub I, we're picking one of the t's, okay? So like say t sub 1, and we're taking the partial of u with respect to that one. And we work through that, and then we could do it for T2, and then T3, and then T4, etc., etc., etc. And we could take any of the partial derivatives that we want using this general formula. The tree diagrams will also work for these general formulas, as we're going to see in the next example. So I think once we actually see one of these in action, it looks a little bit more manageable than this general formula does. So we have our function u in terms of x, y, and z. X, y, and z are functions of r, s, and t. So we're going to find partial u with respect to s at this value when r is 2, s is 1, t is 0. So I'm going to draw the tree diagram. So we're going to get u is at the top. Let's spread these out a little bit. U is in terms of x, y, and z. Those are each in terms of r, s, and t. Okay. So now we're going to find the partial of u with respect to s. So we're going to follow the paths here till we get to the s's. And we can put the partial derivatives that go along with this. So that's partial u respect to x, partial x respect to s, partial u respect to y, partial y respect to s, partial u respect to z, partial z respect to s, that connect the variables together. And now we multiply down and then add across. So partial u with respect to s, partial u with x, partial x with s, plus partial u with y, times partial y with s, plus partial u with z, times partial z with s. And that's going to be our chain rule formula, just in general here, for this case. So now we need to get all of these different partial derivatives, put them all in this specific order, and then we can sub in the values as we go in here. So we're going to have, so partial u respect to s. So with respect to x, we get 4x cubed y plus 0, because there's no x's over there, times, with respect to s, just r e to the t, plus, partial with respect to y, we get x to the 4th plus 2yz cubed, times partial of y with respect to s, that's 2rs e to the negative t, plus partial with respect to z, we get a 0 here, and then a 3y squared z squared, times partial z with respect to s, that's r squared sine of t. Right. Now, we could substitute these formulas into this, but that's going to make it look really messy. It's going to take up a lot of space to sub in all those x, y, and z formulas. And we know that we just want to sub in values anyways. So instead, let's figure out what x, y, and z are for these values of r, s, and t. Okay, so notice when r is 2, s is 1, and t is 0, x is 2 times 1 times e to the 0, which is just 2. Y is 2 times 1 squared, which is just 1, e to the 0, which is also 2. And z is 4 times 1 times sine of 0, which is 0. So we have r is 2, s is 1, t is 0, x is 2, y is 2, z is 0. So we've got all of our numerical values here. Now we can just substitute those into this formula instead of trying to convert it. So partial u with respect to s evaluated at r is 2, s is 1, t is 0 equals, let's see. So anything with a t is going to be a 0. Anything with a z is going to be a 0. So that's going to help us here. Not for this one, though. So that's going to be 4 times 2 cubed is 8. Y is 2. And then 2e to the 0. Plus 2 to the 4th is 16. Plus anything times 0 is 0. So that's a 0. Plus 2 times 1 e to the 0. Plus, this has a 0 in it, so that's a 0. Sine of 0 is going to be 0. So let's see what we have left. 8 times 8 is 64 times 2 plus 16 times 4. So that's 128 plus 64, which is 192. So we get the value of the partial derivative of u with respect to s, specifically at these coordinates when r is 2, s is 1, t is 0, okay, or at the point 2, 2, 0 in terms of x, y, z. The value of the partial derivative is 192. The last thing that we're going to look at in this section is we're going to draw a little bit more connection between the work we had done back in Calc 1 and some of this partial derivative work. It's kind of interesting. We're going to be able to see how this does connect with the concept of implicit differentiation. So implicit differentiation, you see back in Calc 1, is the idea of taking a derivative of a function, y is a function of x, but it's not defined explicitly. So the x's and y's are like intermingling with each other in an equation. It's not y equals some x's, like isolated. Before, we had to use implicit differentiation. Now, we have partial derivatives to be able to help us with this process. So let's take a look at what the connection is. So suppose that an equation has the form big F of xy equals 0, defines y implicitly as a differentiable function of x. Okay, so y implicitly as a differentiable function of x. Okay, so y equals f of x. So big F of x comma f of x instead of y equals 0 for all x in the domain of f. Then if we apply case 1 of the chain rule, we apply case 1 of the chain rule. So if we go back really quickly, that's right here. Partial z with respect to t is equal to the product of these partials plus the product of these partials. If we go and apply that directly here, so we're going to get partial of big F with respect to x times derivative of x with respect to x plus partial big F respect to y times derivative of y with respect to x equals 0. Okay, so we had a function in terms of x and y, which y is also a function of x. So x is the independent variable here. It is also an intermediate variable. But we get this formula for that chain rule. Now, derivative of x with respect to x is just 1. So note dx is 1. So what this means is this one essentially won't show up. All we have isolated right here is the partial f respect to x. So if that partial derivative, partial f with respect to x, is not equal to 0, oh, excuse me, sorry, not this one, with respect to y. If this partial is not equal to 0, we're going to be able to divide by it. Now, why would we do that? Well, because we're going to get partial f respect to x times 1 plus partial f respect to y dy dx equals 0. Subtract this one over. So we get partial f respect to y times dy dx equals negative partial f respect to x. Now divide this under here because it's non-zero. So as long as it's non-zero, this will work. And we get dy dx equals negative partial f respect to x over partial f respect to y. Or in our more common terminology, this would be negative fx over fy. And this expression here, this dy dx, this is not a partial derivative. This is not a multivariate derivative. This is the good old classic derivative of y with respect to x, f prime of x, that whole thing from Calc 1. This is a Calc 1 derivative that we can find using a Calc 3 technique by taking the partial with respect to x and with respect to y and putting them in this arrangement as a fraction with a negative in front. So let's try this out so that we can see how this would work. Now, what I want to do first is I want to show the old way. So like the original way that you would compute using implicit differentiation. So what we would do is we would take the derivative term by term. We would get 3x squared plus 3y squared dy dx equals, that's a product rule here, so 6x dy dx plus 6y. We would need to isolate these terms. So I would move this one over here, move this over there to get it out of the way. So we would have 3y squared dy dx minus 6x dy dx equals negative 3x squared minus plus 6y. And then factor out the dy dx. We're left with 3y squared minus 6x equals negative 3x squared plus 6y. And then divide. So we would get dy dx is negative 3x squared plus 6y over 3y squared minus 6x. Okay, or some version of that, right? We can take out the common factor of 3 to get negative x squared plus 2y over y squared minus 2x. And that would be our derivative found using implicit differentiation. But of course, we don't want to have to use implicit differentiation anymore. We want to use this Calc 3 technique using this formula. So we need to move everything to one side because we have to have everything set equal to 0. So This is so the new way. So we're going to move everything over. So x cubed plus y cubed minus 6xy equals 0. And now we're going to take the partial derivatives. So fx of this. Okay, so this function right here, this is f of xy. So fx is going to be 3x squared minus 6y. Fy will be 3y squared minus 6x. So dy dx will be negative fx over fy. And we can go ahead, we can get rid of the 3. Let's distribute this negative. So we'll get negative x squared plus 2y over y squared minus 2x. And as you can see, it's exactly the same in far fewer steps and far simpler steps. So obviously, when you're learning implicit differentiation the first time, there's no way that we can teach you the entire concept of partial differentiation and functions of multiple variables and all of that stuff just to get you to take a simpler implicit derivative. But now that we have these tools, we can start applying them not only to functions like we've seen in this chapter, but to implicitly defined functions and formulas and equations like this. So we're kind of adding to our toolkit here more and more things that we can do with these partial derivatives. But that brings us to the end of this section, and I will talk with you all very soon in the next.